Thank you. All right, so welcome everyone. I'm just here to talk about, well, I named it the real reason FP matters, and then only after that I realized there are papers and talks that already says the reason FP matters. That's a little embarrassing. Yeah, but let's get started. So about me, I actually have a major in economics. I'm mostly self-taught. And I mostly worked in startup engineers. Right now, I'm working at a C-stage startup. So just to share my perspective, for me, shipping features as soon as possible while maintaining correctness is paramount. That is actually all I care about. And then, well, FP has this image where you don't really do too much with FP. It's all academic. And then I just wanted to talk about, okay, why you actually want to care about FP. When you're in my position. So a little bit more, I have mostly done FP Scala in my career, and I've mostly done payments. It just happens to be. So today I'll talk about 5 things. First, I will talk about the purpose of FP as I see it, how FP works, and 2 major themes of FP also as I see it, and a real-life application of the 2 major themes and your takeaway. So let's start with FP. What is FP? I'll give you the easiest half definition of FP in the world. FP is a programming paradigm. This actually is enough to know why FP matters. Because, okay, if you look at paradigm, what is paradigm? Well, paradigms have a shared purpose. So a programming paradigm it's not math. A programming paradigm is not math. But I kind of see it as an invention, a tool that we choose to use. But why do we choose to use a particular paradigm or any paradigm at all? Is to manage complexity and cognitive load. So I'm going to look at FP in this lens. So that's my goal. So, okay, to achieve this goal, I'm just gonna try to describe the mechanism of how FP works in a simple manner. So this is my example. Let's say you have these 2 values in your head. In your code. Like, because I'm working at payments, you have a price and a tax for it. And let's say you want to display the total the consumer has to pay in 5 different places. So I would do it this way. I would sum these 2 values up, and then I would just use this one value over and over in multiple places. But let's kind of think about like what's going on in your head. So in the beginning, you had 2 items in your head. Like you have to track 2 things in your head, in your working memory. If you sum it up, it becomes 1 thing in your head. So your head your brain has to track 1 less item. So that's how I see as a mechanism of how FP works towards the goal of less cognitive load. So here goes my thesis. Values can compose, and some compositional patterns of values, they end up with less complexity than the sum of the complexity of the original values. It's kind of long, but I'm going to try to break it down. Let's look at the first part. Values can compose. Okay, so I guess it's kind of obvious, but it's okay. Values can compose, but what am I trying to say here? Like, what about others? Others accumulate. So what are these others? So these non-value concepts or ideas, they don't compose if they're not values. So concrete examples would be your try-catch statements, your state changes, your class definitions. If you have like 2 classes, you cannot compose them. Or even recursions. If you have like 2, for example, if you have 2 recursive functions that go through like 1 data structure, you cannot compose these functions in a way that you traverse this structure only once. is impossible. You have to traverse at least 2 times. So recursion itself is not composable. So these things are not values. You cannot compose them. So what I see as the first theme of FP, I think is reification, which is a way of saying if you can compose non-values, you turn these non-values into values. And reification is actually a very common theme. It's not really exclusive to FP. So it's just I'm not gonna go into like everything here, but like it's very common. As in, if you have this concept of more than one values, then you get a list or an array. If you have this concept of last in first out or first in first out, you have a stack or a queue. If you have place in memory, there's an abstract idea. You have your pointer, and so on and so forth. The last one is not even programming language, but a change in a code base is you can kind of reify it into a Git commit. So what I'm trying to say here is reification itself is everywhere. However, in functional programming is we kind of push this a little further, and then we try to reify everything. So I'm trying to go like a little basic here. So absence of value is option. I'm not gonna go through everything, but like the point is we try to reify a lot of things. And then this is like slightly more advanced. Probably to the audience here, it's not gonna be very advanced, even these ones. But for those who don't know, we really have reification for a lot of concepts in FP. So that is what I think of as the first theme of FP. Now let's go to the second part. So some composition patterns of values, they end up with less complexity than the sum of the complexity of the original values. It's quite a mouthful. But what I'm trying to say here is actually this. Not all compositions, they help in reducing your cognitive load. And this is probably, you can relate to this example if you did JavaScript programming for a little bit ago. Well, this is actually interesting in that you're passing functions into functions as higher order functions, and you're composing functions in a way, but if you don't count the side effects. But this shape itself, they're not composing in a way that actually helps reduce cognitive load. So what actually ended up happening is people, they invented or they decided to reify the shape of a callback into a value that is JavaScript promise. And then now they have access to much better composition patterns, and in this case it's monadic. And so yeah, I think composition patterns are the second theme of FP, as I see it. So as an engineer, I'm not really good at math, but I see a lot of ideas from math, including like common type classes. I think they're very useful, and that includes these many common type classes: monoisoning group, functor, monad, applicative, traverse, natural transformations, and like so many of them. Not gonna go through like each one of them because that's not the purpose of the talk. But yeah, so these are the two themes that I identify from functional programming. So now let's move on to the real world problem. So my previous workplace was we were building a payments app. And it just happens to be that we had this entity called order. It's very popular. So it was actually basically needed everywhere. So for display, we wanted to display order on a consumer mobile app that required order and authorizations and the credit cards, the items of the order, and the consumer who ordered it. So they're all related informations, right? It's not all inside one order, but they're like related things. Same goes for a consumer web app. Admin dashboard, you want the order and the merchant associated with the order, the consumer associated with the order, and the credit card associated with the order. If you have merchant tools, merchants, they want to know about the fees they pay for this order. So if it's a merchant dashboard, for example, then you want the fee information associated with the order. And email reports that has like a lot more things. Consumer profiles, because you need to fetch the email address and so on and so forth. So this one entity called order, there were so many places that required order, but with slightly different related data that I also want to fetch from order. I think this is a rather common problem among building software, and that this actually doesn't include where you need the data for business logic purposes. So what ended up is that each of these data requests, either for display or business logic, became one of custom SQL query, because you want it to be performant because it happens often. Or if it's not that it's not really required, then you kind of manually stitch them inside your app. So you grab this here, and then like you get the idea, you grab the other one here, and then you stitch them in the app. Or if that's too much work, then you just end with one query that actually gets everything, and then you discard what you don't want. So it happened to our app, and the bad part, the part I didn't really like, is that it contains zero business logic, just fetching code, and it required full plumbing. In case of display, then it required full plumbing from the REST API all the way down to the DB. For each of the endpoints, rinse and repeat. Not very pleasant, but it's work that needed to be done. So I had this thought, what is the problem? So individual, what I want to fetch, it is not a value. So if I want to fetch the authorization data from the order, well, that idea is not a value, right? So you just cannot compose them. So what's the solution? You just turn them into values and then compose them in a nice way. So what I ended up doing is I built a library. I'm gonna explain in a very high level view like what it does. So it allows you to represent what I want as values. So get the consumer of the order is just order the consumer. It's a value. Get the merchant of the order, same deal. You get order the merchant means get the merchant of the order, or same for like get the profile of the consumer the profile. And now you have these values. I'm not giving you all the details here. You can look it up if you want later. And now we have these values that represent what I want. I can now compose them. So this composition means sequential. So from the order, I want the consumer, and from the consumer, I want the profile. So it means get the consumer and get their profile. We have, and this one is actually similar to joins. So it means sequential composition. I get the consumer first, and then I get the profile of the consumer. There's another pattern, which is, it looks like this. Which is get the consumer and the merchant of the order. So you given one order, you get both the consumer and the merchant is in parallel. It's parallel composition. And and then I'm just trying to show here that you can actually compose them in arbitrary depth and like with arbitrary mix and match of these sequential and parallel compositions. Okay, so this is what I ended up writing. And then let's take a look at, take a step back and then see what happened here. Yep. So what I ended up happening is I reified domain relationship as values. So what I said is what I want to fetch is actually a domain relationship. For example, if I go back here slightly, order the consumer means an order has an associated consumer. In this case, it's optional, but I didn't really include that detail in this talk. But yeah, it is a domain relationship. Order and a consumer has relationships. Consumer and order also has relationships. So this is reified into values. So basically what I did was reified SQL foreign keys as plain Scala values. And then now I discovered this composition patterns of these values. So this this operator that I showed you is goes one layer deep, sequential, and this one is again from the same level, is parallel. So yeah, this is a library that I wrote 2.5 years ago. What I want can be expressed through relation composition, and then the library optimizes the execution either using zQuery or fetch. If you're using Scala, then you might already heard of zQuery or fetch. If you haven't, then it's Haskell-like, if you know about Haskell, or if you're from JavaScript land, then it's like a data loader. So this query, I guess, is actually running through these libraries, and you get automatic batching, automatic parallelization, and all these benefits. So what ended up happening in the code base is we have no n+1 query problem by default anywhere, because most of the data fetching is actually done here. And I just wanted to mention that this library happens to integrate really well with the Scala's Caliban GraphQL library. And then we expose GraphQL to the front end, and we just by default has no n+1 query problem with our whole GraphQL query. So we just write it one-liner, and then no n+1 is auto-batching. So we actually achieved reduced complexity here. So we ended up not writing massive amounts of SQL. So we avoided n+1 query problem. We avoided overfetching. We didn't have to write custom queries for performance. And our GraphQL resolvers are one-liners. I wouldn't say like super fully optimized, but optimized enough by the data loader pattern. And then our backend has no n+1 query problem now. It's pretty easy to write queries with. So that is my, okay, so I have about 2 minutes. That is my experience following this two pattern, which is following these two themes. One is reification, and then one is composition patterns. So I want to be very honest here, and then I have added this slide called the catch. This catch is about FP. So reification and composition patterns, they are, I said as if they're like solving all problems, but they actually do come with their own problems too, which is you are trading long-term memory with short-term memory. You're trading long-term memory load with working memory load, which is to say, you learn it once, it's difficult to learn. So you're loading information to long-term memory. And then that helps you to lower your working cognitive load, working memory cognitive load. So this actually brings one of the criticism that happens like all the time, which is FP is hard. FP is hard because you have to learn more things than the bare absolute minimum that you need to learn. So nullability, for example, is a fact in life. You have to learn it. Doesn't matter the paradigm. But option or maybe, they're not a fact in life. So you gotta learn them additionally. So that is, you have to pay the price in terms of long-term memory. For when you work with them, your working memory is you need to track less items while you work with them. And there's another trade-off that you have to make with reification in some of the platforms, which is cost allocation to do that. Okay, so I just got a very scientific diagram here to give you a understanding of like when you want to pay the price of reification and composition patterns here. So it's if you have a compositional approach, then in my opinion, you have to pay upfront a lot of learning. So you have to pay this cost upfront, but then as the number of things grows in your code base or in your scope, the complexity or the cognitive load in your head grows slower. And the non-compositional approach, because they don't disappear, they accumulate. It becomes more expensive despite being cheaper in the first place. So for each of the items you might choose to go with either strategy. So you might want to, for null, for example, you might want non-compositional, depending on your code base and your teammates' skill level or many other factors. Okay, so just to wrap up, how to control complexity with FP. Identify what's accumulating in your head. Is you feel overloaded, try to identify, pin it down, and then try reify it into values, find patterns for composition, and then you pay your upfront learning cost, what it is, and then you can lower your ongoing working memory load. And so this call to action, what are you tracking mentally? Like what items are in your head right now? And find out what doesn't compose, and then write it down, search how others reified it. I showed you there are so many kinds of reifications in FP, and then you learn the composition patterns. So thank you very much. That's my talk. Before I end, sorry, I'm over time. I really recommend you listen to this talk. It's on YouTube. What every programmer should know about cognition. It actually happens to be in Lambda days as well, three years ago. It's an excellent talk. And here's the GitHub link for the library that I introduced. So thank you very much.
Thank you very much. Okay.